Swayam Prabha. Digital India. Educated India.
So, in today's class, we will continue our discussion on VAMS analytics. We will look at another analytic which is to do with protection, because since this is a protection course, we are looking specifically at protection analytics. Last time we saw an analytic which was more in the historian or offline mode, which was the vulnerability analysis of distance relaying. This one is also to do with distance relaying, and this one also addresses that one. That analytic was sort of a post facto or post mortem kind of analysis, where you take data from distance relays, you analyze it. We saw a video on that, which relays are vulnerable, and then the relaying engineer or the protection engineer comes in and then tries to change the, or rather will change the settings to make the relays less vulnerable to events that we discussed. So, today's analytic is more of an online analytic, and it is a closed loop analytic. The other two that we saw were we just took the data and analyzed it, and then it was left to the operators, the system operator or the control room operator to take appropriate action. Here this is an closed loop analytic which will take data from the PMUs, do the analysis, and then send the decision back to the relay also. So, in that sense, it is a more advanced sort of analytic. So, the analytic is titled PMU Supervised Backup Protection Disk Scheme for Zone-3 of Stepped Distance Relays. So, we have seen when we did distance relays, how a distance relay performs the function of primary protection of a transmission line. A distance relay can also be used to protect other equipment, but here we are talking specifically of transmission lines. So, the distance relay performs the function of primary protection, which is the zone 1 of distance relay, and then also remote backup protection, which is the adjacent lines also. If their protection or if their primary protection like their zone 1 relays fail, then this can provide a backup protection for those transmission lines as well. So, since it has to perform this, it is given multiple zones of protection. We saw that those are known as, that is why it is also known as stepped protection. Stepped because though we have discussed this earlier, it is worth repeating so that the concept is not lost. Okay. So, we saw that if this is a transmission line and this is the adjacent line or lines, or it could also be a parallel line. So, if there is a relay R1 here, then its primary zone of protection is 80% of line 1. So, this is the zone 1. Then after this I am drawing in terms of the line distances. Then after about 80%, zone 2 will start, which will go up to either 120% or of this line, or up to 50%. Let us say if the lines are short, then it goes up to 50%, and then the next longest line. So, this is zone 1, zone 2 and zone 3. Okay. These steps are in terms of the time. this is in terms of the distance, this axis is in terms of the distance, this axis is in terms of time. So, in zone 1 there is no intentional time delay. Zone 2 is usually 2 CTI, so about 500, I am sorry 1 CTI, so 250 milliseconds, 1 coordination time interval, so 250 milliseconds, and this is anything greater than 2 CTI. So, it could be 500 milliseconds or greater, it can be, usually it is set to around 1 second, can be higher also, up to 90 cycles also. Okay, means the highest setting is around of that region, which is 1.8 seconds for a 50 hertz system. Okay. And in terms of the characteristic, then it looks, as we seen last time also, it looks if it is a quadrilateral characteristic, then say this is zone 1, this is the line, the transmission line, this is zone 1, about 80%, then you have zone 2, this is the R and X plane, this is the X axis, X meaning the impedance axis, and then this is zone 3. Okay. We also did see that if the longest line is longest adjacent line is very long, it could be and when we say the adjacent line, it could also mean the parallel line is very long, then this area becomes very large, this area, the zone 3 region becomes very large, and then we could lead to other problems like load encroachment and vulnerability to power swings, etc. Okay, we will go back to our presentation. So, zone 1 again just to repeat, zone 1 provides the fastest protection, there is no intentional time delay, it is not slowed down for any reason, and it covers about 80 to 85% of the line length. The reasons we saw, the inaccuracies in the line model, the inaccuracies with the sensors themselves, etc. So, you generally limit it to 80 to 85% of the line length. Then zone 2 depending on the adjacent line, if it is too small or of reasonable length, then it is set either to 120% or 150% of the primary line impedance. It also provides this provides primary aim is to provide the backup protection for the remaining 15% or 20% of this of its primary line and also the adjacent line. Okay, because you can't leave that 15% unprotected. So, you have to provide a slower protection there. And then the zone 3, which provides backup protection to the longest line, longest adjacent line. Okay. Now, this there are also other zones like zone 4, zone 5 and all that, but they are not very frequently used and very commonly used. They are used, but zone 1, zone 2 and zone 3 are definitely used. So, we will restrict our discussion to those zones of protection. Okay. So, what events affect distance relays? Okay. So, after a fault, generally after some event like a fault or throw off of a large load, there may be some oscillations that are noticed or that result, which are known as power swings. Okay. Now, on the we saw how in the video also last time how on the RX plane how they how if your normal load impedance is somewhere outside, it will be outside of your relay characteristic. During power swings, this starts oscillating here. Those power oscillations appear as oscillations here on the RX plane, and then if they encroach this characteristic for a long enough time, then long enough time meaning if they stay within that characteristic for a time greater than this time, that is 500 milliseconds or 1 second, whatever the relay setting that is, then the relay will issue a trip command, because it has no way of knowing whether that event is a fault or a power swing. okay, because that is the only input that is available to the relay, that impedance. Okay, it sees that apparent impedance, that is why we call it a distance relay. So, this is what it says: if the impedance swing stays in the relay trajectory for a sufficiently long time, the relay will issue a trip decision. Now, this swing may be a stable swing or an unstable swing. Okay. If it is a stable swing, then it will make a I mean, it will result in unnecessarily tripping. Also, if it is an unstable swing, then you may not, though it may, in an unstable swing, you will eventually have to open some line depending on where the electrical center is and all that. We saw that, we discussed that in the class on distance relays, but it may not be at the point that you desire. So, in both cases, if it is not a fault, if it is a power swing, then the relay has to be blocked from operating, or the trip has to be blocked. Okay. There are ways of doing this conventionally, like blinders, etc., and then the time taken to cross that, but then again this is based on the setting of those blinders is based on simulations, which there are blinders that can be put on both sides. You have blinders like this, okay, or you can have a single blinder or blinders, and then the time taken by the impedance to cross this is calculated, because you start the timer here and then close it here and here, and then calculate the time taken. This of course, but it can be done only on the basis of simulations. Okay. If it is slower than a certain time, then you know that it is a swing. Otherwise, for a fault it will cross almost instantaneously. But you carry out the simulations and see what is the fastest swing, and then set this below that or just below, at that point. Okay. But again, as we can see or imagine, this is dependent on carrying out multiple runs, multiple simulations, and can be difficult to set. That is why there are, even though there are blinders and power swing blocking, other power swing blocking techniques, generally when the blackouts do occur, they are successful many a times, but when they are unsuccessful, it can lead to tripping, unwanted or unnecessary tripping of important lines, or lines which could be important, and then lead to cascade tripping and blackouts, etc. So, if it is a power swing, then can we use the information from last time we saw that we have classified the relays as vulnerable, but can we use the same information or information processed in a different fashion to block the relay from operating if it is some event other than a fault. Okay. Once again a look at the strengths and weaknesses of the distance relay in light of this discussion. The strength of course is that unlike a overcurrent relay, this relay distance relay, since it uses the V by I in some form or the other, it is or the apparent impedance. Once we say impedance, it is a phasor. So, it is both magnitude and angle, and with angle comes direction. So, it is directional, inherently directional in nature. It is it does not require it works on local information only. So, of course, that is an advantage as well as a disadvantage, because it does not have information from the other end. It can be a disadvantage, but the advantage is that it does not require a communication channel and hence is immune to communication system failures. And the impedance function is or the discriminant that we call in this case is reasonably accurate. So, though it is prone to other effects like underreach, overreach, we saw in our discussion on distance relays, it is reasonably accurate, especially when compared to an overcurrent relay. Okay. Again, that it works only on local measurements and not global measurements is also a disadvantage, because then it becomes prone to maloperation, because it cannot sometimes very accurately distinguish between other power system events and faults. Okay. And what are those events? We saw that they could be power swings, then load encroachment is a problem. There are ways of overcoming that, but they are not foolproof in a sense. And then low voltage conditions, because if the voltage remains depressed for a long time, it is, since the impedance measurement takes just, we have seen that I mean, in its most simplistic form, VA by IA, say, is XZ1. This is what is the measure. So, this if VA goes down, and even though the current may not be the actual fault current, it could still come in the zone of, especially in zone 3. Okay, what is the principle of we will see the actual scheme, but what is the basic principle of this scheme that has been implemented here. So, here the PMU based analytics or the synchrophasor analytics are combined with zone 3 protection. Okay. And zone 3, why zone 3? Because it is most vulnerable to the faults that we, conditions that we listed here, that is namely load encroachment, power swings, low voltage condition and all that. There is an analytic which works for zone 1 and zone 2 also, but it is a reasonably higher level analytic, and which we will not be discussing in specifically in this class. Okay, so the principle here is design and control principle is used to improve the security of the zone 3 without compromising on the dependability. If you remember, one of the first few classes that we did, we described the attributes of protection: security, dependability, reliability, sensitivity, selectivity. So, in that, dependability of course is the characterizes the correct operation of the relay. Does it trip when it is required to trip? Okay. So, and security is of course the characterizes the incorrect operation, when means does it not trip when not required to trip. Okay. So, that so this scheme will not affect the dependability. The dependability will be as same as before, but it will improve the security, because we are not doing anything to enhance the tripping of the correct tripping of the relay, but what we are doing is we are blocking the unwanted tripping. So, we are improving the security without compromising on the dependability of that relay. Okay. So, if your communication network or your PMUs or your WAM, in general your WAM's infrastructure does not perform up to expectation, or does not poorly performs, then it will degrade the security of the scheme. Okay. But dependability will not be compromised. We will see how. So, dependability will be the same as before. So, even if the scheme fails, your fallback is the earlier relay itself. So, whatever is the dependability that you got, you will still get, but you will not be able to enhance the security. Okay. So, the principle is that here, since the zone 3 relay has a greater delay. So, what we saw is from anywhere from 500 to 900 milliseconds. So, if you can confirm that there is no other abnormal event and this relay has picked up only due to fault, then we can give an accelerated trip signal also. Okay. Something like we provide zone acceleration for zone 1 by taking input from the other relay. Similarly, here we can provide some acceleration for zone 3 time also, since it need not wait out the whole time if the fault is confirmed. Okay. If again rephrasing this, if a fault is not observed in any line subsystem, then a assert block signal can be shown. Okay. There are three classes of signals here: assert, trip and assert block. Assert trip means it will accelerate the trip. Assert block means it will block the trip. If fault there is no fault that is confirmed by the analytic, then it will issue an assert block, so that the relay does not maloperate. And if there is, say, the communication system is down, or there is a PMU data is not received due to some reason, then it goes to the enable trip, okay, which is the default. There is no in which case there is no supervision, and there is no as we said, there is no enhancement of security, but the dependability will not be compromised. Okay, this figure we have seen in the architecture, that how the hierarchy is, and where the this shows also some sort of latency, where about 100 milliseconds to 1 second time you have at the local LDC level, the load dispatch or the regional load dispatch center. You have the the time frame is about 1 second, which fits neatly into the zone 3 kind of time also. That is one reason why for this scheme at least, the zone 3 operating, because of the latencies of the communication and the analytic itself taking time to come up with a decision, and the zone 3 of that of distance relays is supervised. Okay, because for other zones you will require some kind of prediction, which is not handled by this analytic. Okay, so one of the schemes is the PMU will transmit the phasors, that is the line and line currents and the line or bus voltages to the PDC, which can be located at the state load dispatch, regional load dispatch or the national load dispatch center. Then we saw that one of the functions of the PMU is to align all these and create a time snapshot of the system. Then here in this scheme, since it is used for protection applications, the type of PMU which is preferred to be used is P type, because we saw that since the filtering requirements are lesser for a 2 by FS versus 5 by FS, are lesser for the P type, the time delays associated will also be less. Though metering type will be more accurate, the M type will be more accurate, but here we can compromise a bit of accuracy for speed. Okay, the trade-off is acceptable in this case. Okay, so also the PMU should be preferably connected to protection cores to avoid saturation. Okay, since the time of operation is larger, so here there is a chance that the CTs could saturate. If so, to avoid that, protection type CTs with higher knee point and which can support a higher knee point are preferred. Okay, so the next thing is this is the figure 2 shows the how the information and decision will flow happens from the network. This cloud represents the network, and depending on the PMUs that are placed all over the network, and the data that is being transmitted, the PDC will assemble, as we said, the snapshot. The decision is made by the zone 3 analytic, which is running on the server there, and then depending on the results of that analysis, either a trip or a block will be issued, and then this will be relayed back to the substation host computer, and then from that to that particular relay, whether it has to be enabled or blocked. Okay, so the supervisory analytic is located at the lowest level of the hierarchy, could be the state load dispatch center or the regional load dispatch center, as the case may be. And from the SLDC, where the PDC is located, the signal is transmitted back to the substation host computer using UDP, Universal Datagram Protocol, TCP/IP, or some proprietary system. Usually either UDP or TCP/IP is used. So UDP may be preferred as it reduces the latency and the time, because here it does not wait for handshaking and all that. So though it is a less reliable protocol, but for this case the trade-off may be accepted. Okay, so here as we said, there are three decisions that are made. So the decision that is made could be enable trip, assert block, and assert trip. So enable trip is the setting which is which enables the default kind of setting where there is no supervision. Okay. So, whatever is their original setting or original system or original relay, it will continue to work in the same fashion. There is no supervision, so it acts as if as per its inherent setting and logic. And the analytic which is located or which is hosted at the SLDC or along with the PDC, it is time stamped with the signal. So, because it has to, the substation host will have to figure out how is the signal current or no, or should that that signal itself, which is whatever it is, could be enable trip, assert trip, or assert block, is it the latest, or it should be discarded. So, for that it has to be time stamped and compared with the current time at the substation end, and at the substation end also this signal is generated locally. Okay. So, the second one is the assert block. This is issued when the analytic has of course ascertained that there is no fault on the transmission lines or lines that it is supervising, and the relay can be blocked from operation. Okay. So, the the relay which has picked up for on zone 3, it has not issued the trip because the timer has to still run out, then that operation is blocked. Okay. Once again, this signal is time stamped with the GPS time of the time snapshot of synchro phases, which is streamed by the PDC. So, whenever it assembles that time snapshot, the time also is included in that. Okay. So, whatever is the PDC time stamp, that will be associated. Okay. So, for assert trip, this of course, these two are the heart of the thing, because enable trip will set it to the default setting, but assert block will block it in case there is no fault on the system. Okay. So, if there is no, if it observes either a power swing or a load encroachment or low voltage condition, then it will issue an assert block. Okay. Assert trip can be optional, because if fault is observed, then whether to accelerate zone 3 or leave it to operate in its own time is an optional decision. You can choose either, but the first two will be implemented as part of the. Okay. So, what are the major attributes of the decision signal that is sent back to the substation host computer? First of all, the decision itself, whether it is enable trip or assert block or assert trip. Then what is the time of that, because the time it can wait only for a few cycles before it discards that decision. So, the time by comparing it to the current time. So, what is the time ID of that decision, and then what is the destination substation ID and the destination relay ID. Okay. Which substation should this this signal go to, and within that substation which relay has to be blocked or allowed to trip. Okay. So, these four attributes are the important attributes of that signal. So, this is how it works. This is the substation static data, or rather the network data which is got from the substation here. Okay. Then from the PDC, the zone 3 analytic works. Okay. Here this will the PMU is not shown here, only the scheme is shown. The PMU architecture is there in the earlier slide, and then from here this will issue a message which will have the decision, which is assert trip or enable trip or assert block, the timestamp. Timestamp is not mentioned here, but there will be the timestamp also, and then the IDs of the substation and the relay. Okay. Then from the communication network, it will go to the substation host computer, which is there in every substation, and then what it will do is it will take the current time, which is the GPS time, compare it to the timestamp and see whether the decision itself is current or no, and then extract the message. First extract the timestamp and compare it to the current time, then extract the decision whether it is whatever, the enable trip, the assert block or the assert trip, and then either go ahead with either implementing it or ignore it. If the time has elapsed, the wait time has elapsed, then it may ignore the decision also. But if it decides to implement, then it has to send it to the relevant relay, whether it goes to in that substation there may be whatever 8 relays, and this shows 5 relays, and whether it has to go to relay 3, 4 or whichever relay, depending on the ID, it will do the either tripping or block or enable tripping or blocking. Okay. So, now this is a typical scheme. I mean, it may not be representative of some actual system, but this is a very typical kind of scheme where you have 3 parallel lines between bus 1 and bus 2, and then 3 lines feeding bus 1 and 2 lines feeding bus 2. Okay. So, here you have got transmission line, say we can take as an example transmission line 1. So, the primary relays for transmission line 1, this is the transmission line 1, and the primary relays are R1 and R2. Okay. So, now what are the backup relays associated with R1? Okay. If this relay fails, then which are the relays which are blocking, which are backing up, backing up this relay. So, these are this relay R3, R4, R5, R9 and R10. Okay, maybe I should have drawn them with a different color, but anyway you get the concept. So, this relay is okay. This and this. Okay. So, these are the backup relays for R1. Okay. And the backup relays for R2 on the other hand are these R6, R7 and these 2 relays R8 and R9. Okay. So, these are listed here. Okay. So, if also on the other hand, if you take one relay, so this is the line kind of approach. If you take R3, then it is acting as backup for R1, R8, R10, okay, and also R1, R8, R10 and R11, R12 and R13, okay, of these 2. I could not find those. Okay. I will just I think rub them out to make it more clear. Okay. So, if I talk of this relay, then it acts as backup relay for R1, R8, R10, R12 and R13. Okay. These are the adjacent lines for this TL4, okay, and it is doing a backup function for those relays. Okay. Then on any what it means is that if for a fault on TL1, TL2, TL3, TL5, TL6, if its primary relays fail to operate, then R5 has to, or sorry, R3 has to operate. Okay. Now, how do we implement a differential protection logic? As the name suggests, it will be based on comparison of the 2 line currents as measured by the 2 end PMUs at the 2 ends. Now, this can be implemented by using either positive, negative or 0 sequence currents or all of them also. Okay. So, a fault which has not been cleared by the primary protection can be detected by the differential protection logic. You have PMUs at two ends, we are getting the current phases. So, that can be those can be compared using their sequence components. So, this we discussed, since the zone 3 time delay setting is of the order of 1 second, it could be 800 milliseconds, 900 milliseconds, it is generally of that order, and PMU reporting time is about, for us it is about 40 milliseconds, it can be 20 milliseconds also. So, this fault can be detected in multiple frames. This fault can be detected in multiple successive frames. Okay. So, this is how the this is the pi model of the line. There are PMUs at both the ends of the line. So, they may the line is between buses 1 and 2. So, the PMU at 1 will measure V1 and I12. The PMU at 2 will measure V2 and I21. Okay. And this the difference will be in the I12 and I21 will be in the charging currents only. Okay. So, it is designated as I12 series and I2 series current, okay, because there will be some shunt component also. Okay. So, here the psi function is defined as this is to account for the charging currents. Okay. So, the psi function here is defined as JB by 2 into V1 by V2 and JB by 2 into V2 by V1, sorry, into psi V1 V2 is J B by 2 into V1 plus V2, and psi bar V1 2 is J B by 2 into V2 minus V1. Okay. So, how is the fault detection logic using differential currents is implemented here? Here as you can see, the first one is the difference current here. Okay. The numerator will be the difference current. If here if there is no fault on the system, then of course, this current I12 plus I21 minus this the psi 0 will be 0. Okay. And this will be some large value, because it will be the summation of two currents reverse. So, there will be the double of that current plus the charging component as well. Okay. So, if there is a fault, these currents will reverse. Okay. So, the numerator will become very, this is of course demonstrated using only the 0 sequence component. So, the numerator, if in presence of a fault, these currents will reverse. So, you will have first, in the first case, you know, I12 is flowing like this and I21 though is like this. So, it will be minus of I12. So, the directions are reversed. So, the numerator will be close to 0. Okay. Also, we are accounting for the shunt component here, but in the denominator it will be a high value, because you are adding the two. Since this is minus I12, it changes the sign. Okay. Similarly for the positive sequence component, this is the positive sequence differential current. I12 same logic is applied here. Of course, there is a percentage multiplier here. So, that is why it is multiplied by 100, and similarly for the differential current in the negative sequence components. Okay. So, if the differential currents in the three sequence components, that is the positive 0 sequence differential current, positive sequence differential current and negative sequence differential current is less than a certain threshold for each sequence. I mean, you can have different thresholds for different sequences, since the 0 sequence current could be expected to be low. So, you can have different thresholds for different sequence components of the current. If that is low and it is below a certain threshold, say 1 to 10%, then there is no fault on that line. Okay. We are comparing the difference currents, and then it is similar to a current differential protection logic. but a few more few more nuances are added to it. Okay, so what is the finally we will conclude with the methodology. What is the methodology for this implementing this scheme? Okay, so the fault on a designated line, it would be TL1 or a designated relay for that matter. So, TL1 we saw, which was this, no, not this, TL1. Okay. So, for this is the TL1. Okay, for where were we? So, approach will be to monitor the fault on the designated line. Then the primary design attribute is line in this case, and the secondary design attribute is set of the backup relays for that line. Okay, that set we saw. What are the backup relays for line TL1? Okay, for R1 they are R3. So, primary attribute is TL1. The secondary attribute is the set of relays, that is R3, R4, R5, R9, R11. Okay. Then if the differential logic indicates a fault on that line TL1, because we are comparing the difference currents in each sequence component on the two ends of TL1, and then if there is a fault that is indicated by that, if the current is higher than that threshold eta that or epsilon that we have set for each sequence component, then the trip flag is raised for the set of backup relays. Okay. Set of backing up relays for B1 for R1 are or that R1, R3, R4 whatever, R5, R9, R11, and for B2 are R6, R7, R8, R10. Okay. And assert trip, if you choose to implement that, then assert trip decision is obtained by an OR operation. Okay. For the assert trip flags for the lines it is backing up. Okay. So, that is for assert trip if it is chosen to. If the line is indicated to be healthy, then the differential relay indicates the differential protection indicates a healthy line, then the block flag is raised for the union of those two. So, for all these relays, so for all the union of these two B1 and B2, for all these relays, for relays R3, R4, R5, R6, R7, R8, R9, R10, R11, for all the backup relays which are the backup to TL1, the tripping is blocked. On the other hand, if you detect a fault, then the say fault for on relay R3 on the line that is protected by R3, then these relays for example will be set to enable trip. Okay. So, here the block flag will be raised and then the decision will be to block those relays. Okay. So, the second methodology of course is that for a given backup relay, say R3, then perform AND operation on the block flags of the corresponding set of primary lines. Okay. So, what are the set of primary lines for P3? These ones. So, what are the set? These are TL1, TL2, TL3, TL5 and TL6. So, these are the TL5, TL6, TL1, TL2, TL3. So, for R3 here for this relay, if there is a fault detected, then that decision and the decision of relay R3, if that is also indicates a fault, then you go ahead and trip the relays, backup relays associated with those are TL1, 2, 3, 5 and 6. Okay, if it indicates no fault, Then if this logic indicates no fault, then the logic is AND. So what, even if that relay is indicating a trip, and this relay is indicating no trip, so since it is an AND, it will block the relay from operation. Okay. So that's what it says. If the resulting action is affirmative, or the resulting decision is affirmative, assert block is issued, and if the PMU data is unavailable, communication fails, PMU data does not come through, then and the assert trip is not available, then enable it, then go to the default setting, which is enable trip. Okay. Then it will not, there is no supervision, whatever is the decision of those backup relays which is in the set B1 and B2, it will go through with that decision. Okay. So why is that? We talked of timestamp. Okay, why is the timestamp relevant? Those reasons are listed here. So before it sends the decision, it is timestamped with the GPS timestamp for that time snapshot, and then once the decision is received at the substation host computer, it compares that timestamp with the current timestamp. Okay, which is also a GPS time, because that also the substation host computer also gets the GPS time. And if the delay is greater than the threshold, because we have instructed it to wait for certain amount of time, like we had wait time in PMU, PDC, in the PDC, here also there is a certain wait time. Okay. So this is settable, but we have to give this so that to make sure that the decision itself is current. Okay. Otherwise, it will there is no way of knowing when the decision was taken and whether to block or not to block and all that. Okay. So if the delay is greater than a threshold, because it will wait for a certain time, and if the delay is greater than the threshold, then it makes out that this decision is not a current decision, and then it goes to the default setting, which is enable trip. So it will not take any assert trip or assert block decision. Also, if no communication is received, then it assumes that it assumes the default state, which is the enable trip decision. Okay. So what are the typical values of time durations that are associated with this? So here the substation from the substation host computer, the decision is transmitted to the relay, because the relay will also have can be hooked up to the substation host to the substation network or the substation LAN. So what the duration of the assert trip is set to 40 milliseconds. Okay. So if in the next this is to because the next decision will also come through in 40 milliseconds only. So this is set for the duration of one sample in this sense. Okay. So one PMU phasor, that the duration of this assert trip is also set to that. So in the next decision signal, when it is received, if there is no fault, then this will get cleared. The duration of assert block is set to 80 milliseconds. So there are two two signals will be received in this amount. So if in the next time block, there are two time blocks of 40 here. If the next time block assert trip is received, that will override. Okay. Also, any assert trip, that is what we said just now, any new assert trip message gets priority over the running assert block signal. So if a time block, an assert block is running for 80 milliseconds, and after 40 milliseconds the assert trip comes in, it will get priority. Okay. So there can be queued up and valid, less than the time threshold delta station, assert block signals are used to refresh. Okay. So if there is an assert block, then it will keep refreshing. Okay. And if there is of course, if there are no signals received or of the message, or the time is not reliable, then enable trip will be will be the default setting. Okay. So, and also to keep in mind that the time, the decision itself has to travel on the substation LAN. So, whatever is the latency there will also have an effect. Okay. So, what are the some of the performance issues that are there with these with the setup that we have here? We will discuss that. Quickly show a setup which was done to test this, and then we will close this lecture. Here we can see that due to the placement of the PMUs, then the PMUs will transmit to the PDC in the SLDC, and then that will transmit to the PDC in the RLDC. So, the if to create system snapshots at the RLDC level, the latency is higher than the SLDC level. So, there due to aggregation of PMU inputs, the time snapshot creation at the RLDC level takes a longer time than the SLDC level. So, whatever data consolidation or the decision making of this analytic can be achieved at the lowest level possible, that is the SLDC level, it should be done there. Okay. So, this just gives us some reason, the RLDC, some set of due to some communication delays in some part of the network, if some PMUs are not data of some PMU is received with some delay at an RLDC, it will slow down the whole system. So, it is better to attack this at the lower level, which could be the RLDC, I am sorry, the SLDC, and then work on it. Okay. A smaller set of relays, the smaller the set of relays and PMUs involved, the faster will be the decision making. Okay. So, here this is the actual setup here. Okay. Here the PMUs were streaming data to a PDC. This was the architecture of the server and the analytic here, and the Zone-3 analytic worked, and it was implemented here and sent back to the substation client. Okay. This was how it and from the substation host computer, this was the hardware that was used from the substation host computer. This hardware was used for Modbus communication with the relay. Okay. Because the relay will not talk on TCP/IP, it needs protocol conversion to Modbus. Then we use this hardware, and then the decision was conveyed to the relay. Okay. So, to conclude, since the Zone-3 protection is a comparatively slow operating analytic, which delays up to 1 second, the information and information that is obtained from PMUs or synchrophasors can be used to supervise, and the performance can be improved of the distance relay can be improved by gathering information from neighboring buses, PMU or synchrophasor data from neighboring buses. The performance can be improved, and performance in the sense of the security can be improved without compromising on the dependability. So, this ends our discussion on VAMS analytics. Next time we will have a quick look at some unit protection schemes before we end the course.